Hello and welcome to our second video of our Physics 1 playlist. In this video we will be doing all things vectors. So if you haven't watched our first video, which was kinematics, this video is basically just going to be a carry-on and a more in-depth video, hence the subtitle 2D kinematics. So without further ado, let's go ahead and get started on our vectors unit. Just a refresher, a vector is a quantity with both magnitude and direction. So for example, if we were to draw an origin line and label it 0 degrees, and draw a vector line 30 degrees counterclockwise from the origin line with magnitude 2 meters, and let's label this vector r, then vector r would be read as 2 meters and 30 degrees. So when you're adding vectors, you have to take into account magnitude and direction in order to find the resulting vector. And this resulting vector of adding two or more vectors together is called the resultant. So the rule to add vectors visually is to place them head to tail. So let's say, for example, I have these two vectors, the tan one and the red one. In order to add them up, I would place the tan one's head to the red one's tail. So then you would draw the resultant vector from the absolute start point to the absolute end point. However, if you were to take the red vector first and then add the tan one by the method of head to tail, you'd actually find that the resultant vector is the same. So let's write that down. The order at which the vectors are added does not affect the resultant. Now let's talk about vector subtraction. To subtract a vector, add the vector that you are subtracting's opposite. So what does the word opposite mean? As you recall from the kinematics unit, a vector's opposite has the same magnitude, but the angle differs by 180 degrees. So now that we have defined what vector subtraction is, let's do an example that visualizes vector subtraction. So let's say we have vector r and vector s, and we want to find vector r minus vector s. Now, let's just place vector r head to tail with vector s. Now, if you were to draw a vector from the start point of r to the end point of s, you would actually find the resultant, or vector r plus vector s, which is not what we want. Instead, we can choose to think of the expression as vector r plus the opposite of vector s. To draw negative s, you would have its start point in the same location, let it have the same magnitude as vector s, but its angle should differ by 180 degrees. Now I'm just going to draw vector r minus vector s again, just to make things more clear. And this time, when you draw the resultant, it can be read as vector r minus vector s. Alright, so now let's move on to the parallelogram rule. The parallelogram rule is just another way to visualize addition and subtraction of vectors. So what you would do is that you would need to place the vectors tail to tail, and then draw a certain diagonal depending on whether you are adding or subtracting those vectors. So what did that just all mean? Well, let's do an example. Let's say I have vector r and vector s. And now let's draw a parallelogram, or finish the parallelogram. Now, if you were to start a vector at the tails of vector r and s and draw it diagonally to the parallelogram, you would get the resultant of vector r and s. And this makes sense in two ways. The first way is that if you were to rearrange the vectors so that they are placed head to tail, the resultant vector does match up. The second way is that the resultant is kind of going in the same directions for both of the vectors. What I mean by that is that vector s is mainly going in the right direction, and you see that in the resultant, and vector r is going in the downward direction, and you also see that in the resultant. Now I'm just going to draw the same diagram to the side. But what would happen if we drew a vector from the head of one vector to the head of the other one? Now in this case, since the resulting vector is starting at the head of vector s and ending at the head of vector r, the resulting vector will be read as vector r minus vector s. Now you can check this by doing the subtracting visualization method that we did earlier, but you can also see if this logically makes sense. And it does, because vector s is mainly going in the right direction, but the resulting vector is going in the left direction. And vector r is going downward, and the vector is still going downward. So it can logically be read as positive vector r and negative vector s. The next thing that you would need to understand in this unit is vector components. Now, every vector has an x and a y component. So let's just take this arbitrary vector v that I just drew out. This vector v has a vector x component going in the horizontal direction and a vector y component going in the vertical direction. And notice how the vector components line up. The x component is clearly showing how much right vector v is going, while the y component is clearly showing how much up vector v is going. The next topic we will touch upon is called the equilibrant force. Now, the definition of an equilibrant force is that it is equal in magnitude but opposite in direction to all of the other forces acting on this one body. Now, that was quite a mouthful, so let's draw a diagram to represent what this means. So let's say that we have force 1, force 2, and force 3 all acting on one object that results in the object not moving. In other words, the object in the middle is in equilibrium. Now let's describe the situation mathematically. One way you could describe this is that the opposite of force 1 and force 2 summed together is equal to force 3. So basically, these two forces combined is equal to this force, but just in an opposite direction. So let's manipulate this equation really quick. Now we can actually show algebraically that from the equation on the left, we can derive that force 1 is equal to the opposite of the sum of force 2 and force 3. So the sum of force 2 and force 3 is equal in magnitude but opposite in direction to the equilibrant force, force 1. So the last equation that we can derive from this is that force 2 is equal in magnitude but opposite in direction to the sum of force 1 and force 3. Now let's bring up something that we just talked about. Let's see if we can show how this equilibrium concept works by bringing back the parallelogram rule. As you may recall, the parallelogram rule states that the sum extends diagonally from the tails of the two vectors. So let's label this vector force 1 plus force 3. And what do you notice? You notice that this vector sum is exactly opposite to force 2. So it's pretty cool how we just used something that we learned 2 minutes ago to show how this concept works. Now let's get into relative motion. Basically, any quantity of motion is measured relative to a frame of reference. And a frame of reference can literally be anything, and values will change depending on what frame of reference you use. In this example problem, we have a ball A traveling at 4 meters per second in the direction of 0 degrees, and we have a ball B that is traveling 3 meters per second in the same direction. Now, let's say that we want to measure the velocity of ball A relative to ball B. And so this is the format that we would write it in. In the subscript, the frame of reference goes second, while the object you are measuring goes first. So this format can also be written as velocity A minus velocity B. And since the balls are moving in the same direction, this is just simple math where you would do 4 meters per second minus 3 meters per second. And this would result in ball A traveling at 1 meters per second given the frame of reference of ball B. You can also imagine yourself as ball B, seeing ball A traveling at 1 meters per second if you view yourself, ball B, as stationary. Now, the next thing that we want to add in our notes about frame of reference is that the velocity of A relative to C is equal to the velocity of A relative to B plus the velocity of B relative to C. Now, that probably doesn't make much sense, but once we do an example, I think you'll get it. Now, let's say that there's a person moving around on a bus, and that bus is moving along on the road, and we want to find the velocity of the person to the road. The first thing that we would want to do is we would want to label what A, B, and C are. So C would be the road, B would be the bus, and A would be the person. And let's just go ahead and draw a diagram to visualize what's going on. So here you can see me just drawing the road, and then the bus, and of course the person walking on the bus. If the bus was moving at 3 meters per second to the right on the road, and the person was also moving 1 meters per second on the bus, and they're going in the same direction, then that would just be simple math where we would do 3 meters per second plus 1 meters per second equals 4 meters per second. Now, of course, you're probably not going to get a problem this easy on the actual AP exam, but this will probably help you understand the concept better. If you would like me to do a video showing you harder example problems using the vector addition rules that we had earlier in the video, please let me know down in the comments. Now we are down to our very last topic of this unit, which is projectile motion. A projectile is an object that's launched with an initial force and then proceeds under the sole influence of gravity. So just to be clear, we don't really care about what the force is, we really just care what happened to the object. Now I'm just going to draw a scenario of where an object is being launched with a certain force and it lands at the same height that it started at. The first thing you may notice is that the path the object traveled at is a parabola. And this parabolic shape actually goes for any object in a projectile motion problem. The next thing you may notice is that each dashed vertical line represents a certain amount of time. And these time marks are also equal in distance. So what you'll notice is that the object is moving in the same amount of distance in the x direction per second. So we can note that gravity does not affect the object's motion in the x direction. And that makes sense because, as you remember from the first unit, gravity has a force that accelerates 9.8 meters per second downward, so it really should only affect the y component. In other words, we can say that the x component is constant. And we can say that the y component has a constant acceleration downward, which is g. Recall your velocity and distance formulas from last unit. In this unit, you're still going to use these equations. The only thing that's different is that you're going to break up the distance formula into its x and y components, which basically means your horizontal and your vertical components. Now let's include what we know about each component. Well, we know that gravity does not affect the horizontal component, so we can say that the x acceleration equals 0. And what you'll find is that in the x direction, the velocity is constant. And this is because acceleration times time is going to be 0. So the final velocity would just be equal to the initial velocity. Now the x displacement equation is going to be the same idea. After you write out its equation, you'll also notice that the acceleration is going to be 0. So the displacement in the x direction is just going to be initial velocity times time. So in the end, you're left with these formulas in the horizontal direction. Alright, so now let's move on to the vertical components in projectile motion. You know that in the vertical direction, the object is influenced by gravity. So the y component of acceleration would be negative 9.8 meters per second squared, or 9.8 meters per second squared downward, and this is also known as g. And we can use this acceleration and plug it into the y velocity. So let's do that. The velocity of the y component is equal to the initial y velocity plus negative 9.8 times time. And again, it's the same idea for the y displacement. So the displacement of y is equal to the initial y velocity times time plus 1/2 negative 9.8 times time squared. So now I'm just going to write these equations just a little bit bigger so you can read them easier. That was all the topics covered in Physics 1, Unit 2, Vectors, covered in under 15 minutes. Comment down below if you guys would like to see some practice problems or some past AP test problems from this unit. And speaking of AP tests, I got my scores back from Physics 1 and 2, and I got 5 in both. So maybe in the future there'll be some Physics 2 content? Anyways, in the meantime, good luck with physics and subscribe to Sutors. Bye!